All right. Good afternoon slash morning slash good on you for being here today. Today we are going to do kind of integrating things that kind of become logs. But before we go, let's do a joke. Why was the raisin afraid to go swimming? It was afraid of strong currents. Hopefully you get that joke. You either do or you don't. But let's get straight into it. Integrations that make logs. Okay. You guys like my integration? I think that's brilliant. And my log, I think that's brilliant too. Now let's recall a couple things and we're just going to hit a couple examples. So let's recall if we differentiate ln x, we should get 1 on x. Okay. So it makes sense that if we integrate something like 1 on x, which is a hyperbola, by the way, or what some people might call a reciprocal function. It just means that it's kind of like it's been flipped on itself. Instead of x on 1, it's 1 on x. Basically, when there's an x on the bottom, what we're looking for is it's just going to become ln. And here's the difference. It's not just going to become ln x. It's going to become ln the absolute value of x plus c. The reason being is logs are never negative. And so with the reciprocal, they're kind of like equal on both sides of the zero. So, but just remember, we want to take the absolute value of the x. Okay, we don't want any negatives. We may have to integrate between negatives, but we're always going to take the absolute values. Plus c. All right. And if we were to derive an ln of a function, this just becomes f dash x over f of x plus c. Oh no, sorry. Not plus c because we're differentiating. Don't make that mistake. And so if we were to integrate some sort of fraction where the top will look like a derivative of the bottom, then it will become ln of fx plus c. Okay. So I want you guys to write these down, make them nice and pretty. Okay. These are the ones that you will need to memorize. The second one here at the bottom, that's what you'll get in your reference sheet. So you don't have to memorize it, but I would suggest getting very, very familiar with it. Okay. Now that we've got that down, let's hit some examples. Now, for the first two, for A and B, I want you to try on your own. See if you can get there. Okay. Pause the video, have a go. All right. Hopefully you paused. Okay. Now here, it's just going to be the same as 3 times 1 on x dx. So I can just write this as 3, and I know that 1 on x will integrate to ln x. ln x plus c. There you go. So that'll be that. Let me move all this over. Please do not forget your plus c's when dealing with integrations, and especially when they're unbounded. Okay, so there's no a's and b's. Okay, for this one here, let's take a look. Slightly different. We've got different numbers, but if we look at the bottom, if I can get a pen working, if you look at the bottom here, your function, third time's a charm. There you go. If you look at that bottom one there, if fx equals 2, 2x plus 7, what's your f dash x? It just becomes 2. And is that what we have on top? It is. So it's just going to be, this one's going to be a bit more straightforward. It's just going to be ln and my function. So in this case, 2x plus 7, and then that plus c. Okay, hopefully you're starting to see it. If you're not, go back and watch it again, start to make some sense of it. Okay, now let's move down a little bit. Let's go to the mid levels, okay? And then you can see the last one here, it's spicy. So we've got this now. Again, let's take a look at the bottom. And all I'm really looking for, and if you can make a note here, look for these. If the bottom is 1 power greater than the top, I know immediately it's probably going to be some sort of log. Same thing here. This is just x, and then if I differentiate x, it kind of comes like the top. Okay, that's what I've been looking at with all these ones. Okay, so that's kind of my little hint here. If the derivative of the denominator can kind of look like my numerator, that's how it's going to look. So again, if this is my, oh my goodness, if this here is my bottom, if that's my fx, what's my f dash x? It becomes 6x squared. And if you notice here, it's exactly the same as the top. So if my derivative, if it's the derivative over the original, then I know immediately this is just going to be equals to ln of my original. So it's going to be 2x cubed plus 4 plus c. All right, now let's do one that's slightly different here. Now here, if I was to derive the bottom, if that here was now my function, oh puppy, hey buddy. If that's my fx, then my f dash x now is going to become 4. Now you notice here that 4 and 1 are not the same. Okay, so what's happening here is I kind of have to almost divide by 4 because it should be 4 on top, but it's 1. That means I've actually divided it by 4 or times it by a quarter. So this is going to equal to 1/4 ln of my original 4x plus 3. And again, I should be using my absolute values and my plus c. Okay, now let's have a look at the next couple ones and we'll have a bit more practice of those. Okay, almost there, spicy. Okay, now these ones here, this first one can't really, there's 2 terms on the top, so I can't really deal with that yet. But remember, when we've got something like this, we've got a fraction, we can actually separate them. So I'm going to separate them, keep the integration sign here. This is going to be 2 over 3x, and I'm just going to write minus x on 3x dx. Okay, so whenever there's 2 terms on top or we've got like a singular term on the bottom, it kind of lends itself to be separated. So if we now try to separate it, this becomes integration of 2 on 3x minus, and I can cancel out the x's here because they're both common factors. So this would just be 1 on 3. Okay, now, if I was to integrate term by term now, I know this one here is just going to become minus 1 on 3x. Okay, that one's pretty easy. But this one here, I've kind of got a 3x. And if I was to derive it, I should have got 3. Right, but I've kind of got 2. So what I have to do is I have to think, okay, well, what times 3 is going to give me 2? So it's going to be 2 on 3. Or times it by 3 on 2. Of course, this would happen while I'm filming. Okay. So again, here's how I would look at it. It's going to be, if I took the ln here, so this is why it's spicy. If I took the ln here, what I want it to be is I wanted it to be 3 on 3x. But what we have is we have 2 on 3x. So how do I get from 3 to 2? Well, I'd have to multiply it by 2 over 3. Yeah. So in other words, that's what I'm going to take out here. That's what I'm going to take out. So I'm going to have 2 on 3 out here. I'm going to have my ln of 3x. And then I'm going to minus that 1/3 x, and I'm going to plus c. And that would be your answer there. Okay, I'll keep this down here so you can kind of see what I did. All right. This one here is going to be somewhat similar. I'm going to look at the bottom here. Now, all I'm seeing here is if I derive my x squared, I do get some sort of value of x, but it's going to be slightly off, so I'm going to have to make some adjustments. So again, if that's my fx, I need to find my f dash x. And so my f dash x is going to become 4x. So what I need to do is I need to think, okay, how am I going to get from 4x? How do I get that to 5x? And again, it's going to be the same thing. I'm going to times it by 5 on 4. Right? And so that's how I get from 4x to 5x. I need to multiply it by 5 on 4. So this is going to be 5 on 4 ln. Again, the absolute value, it's just going to be my original 2x squared minus 7 plus c. Okay. Now, the reason that those ones are spicy is because you're going to have to find out, how do I make the derivative kind of look like my numerator? Okay, hopefully that's making a little bit of sense, but if you need to, pause it again, go back. And worst comes to worst, if you're not sure if you've done it right, go back and differentiate it. Okay, so if, let's say, for example, I'm working with this, I'll say the y dash now becomes 5 on 4 times, and that would be 4x over 2x squared minus 7. Okay, now if I do this, the 4's cancel out, leaving me with 5x on 2x squared minus 7. And that's exactly what we came up with. We're all good. Yep. And that's a little bit about what this is about. Hopefully that makes sense. And hopefully it's doable. And I'll catch you guys later. Bye-bye.